In this video, we are going to introduce electrochemistry. And before we do that, we're going to review what we already know about reduction and oxidation. We went over this kind of concept when we talked about different types of chemical reactions. And we looked at combustion reactions, we looked at precipitation reactions, or double replacement. And one of the categories we looked at were reduction and oxidation reactions, which we call redox reactions. So this is a quick review of what you hopefully remember from a previous chemistry class. So reactions that transfer an electron between the reactants are referred to as oxidation reduction reactions. We also call them redox for short, because otherwise it's a really long name. The oxidation of an element or a molecule will be the loss of electrons, while the reduction of it will be gaining electrons. Anything that is oxidized will be acting as a reducing agent. If it loses electrons, it is acting as a reducing agent by giving electrons to another molecule. If a molecule is being reduced, it is acting as an oxidizing agent. It gains electrons by oxidizing another molecule and taking those electrons from them. There are a few handy mnemonics to remember this. Oil rig is one of them. I think there's also Leo the lion says grr, but I kind of always get that one mixed up. I know oil rig. It's oxidation is loss. It's of electrons. And reduction is gain. So we have a simple example here. We've got a zinc atom that's in its elemental state. So it has a charge of 0 or an oxidation state of 0. And we have copper plus 2, which is in the plus 2 state. It's an ion, cation. And we'll see a redox reaction occur where electrons flow from the zinc to the copper. And that's going to then create a positive charge on our zinc atom because it has lost electrons. So now there'll be an imbalance where there's more protons than electrons. And we create this zinc plus 2 cation. As that copper cation gains electrons, it becomes actually just a metal. It forms its elemental state of copper with a charge of 0. And we could break this up into half reactions as well. We can call our zinc half reaction the oxidation half reaction. Where our zinc becomes zinc plus 2 electrons. Those 2 electrons that have left our zinc will then go to the copper. And so we can write our reduction half reaction that focuses just on the reduction half of this as our copper plus 2, gaining those 2 electrons and forming copper metal. So to determine if something is oxidized or reduced, we really need to compare their charges or their oxidation states if it doesn't have an overall charge, which is the same thing. So to know if something loses or gains electrons, we compare the oxidation state of the reactant to the product. And if the oxidation state gets more positive, then we know we've lost electrons. And if it gets more negative or if it gets less positive, we know we've gained electrons. So this slide shows the kind of rule set to follow to determine the oxidation state of a molecule and each of the individual elements within that molecule. And so it looks like a lot of rules, but really I think the important part to remember is this piece right here. The oxidation state order for assigning oxidation states for different elements. And so these rules need to be applied in order. They are really showing a priority of how to assign an oxidation state. And the higher the number on this list, the higher the priority. And so we always go in order. A lot of times we're skipping, when we're looking at organic compounds, the first handful of these that deal with metals or elements, and then ions. Ion charges will just be the charge of the ion if it's a monoatomic ion. If it's a polyatomic ion, then the oxidation states of all of the elements need to add up to the overall charge of that ion. And then we've got our group 1 metals will always be +1, then group 2 will be +2. If those are in conflict, we always give priority to the group 1 metal being +1. And then we go to nonmetals, and we follow the priority of fluorine first, being -1, then hydrogen, +1, oxygen, -2, anything in group 7, which is our halogens, being -1. Then we go to group 6A, which will be -2, and 5A, which will be -3. And so by setting up this order, we can determine oxidation states. And we could do a quick example here as a reminder. Let's take, making this up off the top of my head. Let's do H2SO4, sulfuric acid. So this is an organic compound, so this is going to focus on this priority list here. That's our last. We don't have anything that is just an element in its elemental state. We don't have a metal. We don't have a charge on this molecule at all. We don't have group 1 or group 2 metals. And I'm now going to go through this list here in order. So I have no fluorine, but I do have hydrogen. So the first one I'll assign is hydrogen, which will be +1. Going down my list, next is oxygen in priority. So I'll assign that oxygen a -2. That leaves just my sulfur, and I'm going to balance out the charge on these oxidation states, or balance out the oxidation states to equal 0 using that sulfur. So if I have 2 hydrogens and they each have a +1 oxidation state, I have 2 times +1 for a total of +2. I have 4 oxygen atoms, each at -2 oxidation state, for a total of -8. So for this to equal 0, my sulfur charge, and I only have one of them, so it'll be sulfur times 1, +2 -8 has to equal 0. That's going to give us a sulfur oxidation state of +6. So my 6 + 2 would be +8. That would balance out the -8 from the oxygen. So in this way, we can determine oxidation states. I would then, if I was looking at a reaction that compared this to something where on the other side of it we formed, let's say, sulfur dioxide. I don't know if this is actually a reaction. I'm just kind of making it up. Then we would compare the oxidation states of those elements. So we'll ignore hydrogen for here because I didn't put a hydrogen in my product. So determining the oxidation states, oxygen has a higher priority than sulfur, so it'll be -2. That gives me 2 times -2 for a -4. That means that sulfur has to balance out that -4 charge by being +4. So my oxygen doesn't change oxidation state, so it hasn't been oxidized or reduced. But my sulfur is going from a +6 to a +4. And that is a decrease in the amount of positive oxidation state we have. So it has to gain electrons to do that. So this is gaining electrons, therefore it's being reduced. And in this way, I'm going to compare the elements on both sides of my arrow and determine which element is being oxidized and which element is being reduced. And that'll be important for when we move on in the next lecture to how to balance redox reactions. Before reviewing how to balance redox reactions, I want to point out a few common oxidizing and reducing agents. And this is really just so you've got building up a little bit of chemical intuition. I don't expect anyone to memorize this, but it can also be a handy reference when you're working on practice problems later. So here are our common oxidizing agents, and then on the right-hand side, it shows what they are oxidized to, or sorry, reduced to. So that oxidizing agent means it's going to oxidize something else. And so that means it will be reduced. So oxygen, which would have an oxidation state of 0, is being reduced to oxygen -2. And so it's each oxygen atom is gaining 2 electrons. And so this is going to oxidize something by 4 electrons to form those two O-2 atoms. Hydrogen peroxide is another very common oxidizing agent. Our elemental halogens are halogens combined with oxygen, so chlorates and chlorites, or bromides, iodates. Sulfuric acid, as well as sulfites, nitric acid or nitrite. And then manganese oxides and chromium oxides are ones that we'll see a lot for oxidizing agents, things that are easy to reduce. So here's some common reducing agents. We've got hydrogen becoming H+, which demonstrates that that reducing agent, if it's going to let something else gain electrons, give them to it, it's being oxidized. Sorry, can't spell being. And I know that language is a little tricky because it's they're opposite. Something that's oxidized is a reducing agent. And so in this case, these are always going to lose electrons. And so our H2, which is in its elemental state, becomes 2 H+ atoms. That means it's going to lose 2 electrons to form those 2 protons, like this. And so those 2 electrons could then be gained by something that was being reduced. So some of our common ones, hydrogen peroxide is one of our oxidizing agents, but it also works as a reducing agent. Our ammonium and N2H4, and then a number of our anions as well. Some of the anions, like I think the SO3-2, also acts as a reducing agent as well. And then rather than having chromates or manganese oxides, we also have, for reducing agents, it's more common to just see metal cations, especially transition metals or post-transition metals like iron, chromium, and tin.